Can you hear me now? Yes. Okay. Hello, welcome. Thanks for coming, even though it's raining, and thank you for viewing this online. Today is a good day to watch this over YouTube. It's very grey and foggy, rainy here. So this is the fourth lecture of the Smart City series of lectures. We've talked about privacy, security, we've given an overview, and we've mentioned this standardization effort for smart cities called Harmonization of Internet of Things, or IoT Harmonization. And so this lecture, I will present this effort, standardization effort within the IEEE, and why it's needed, what it includes, and what we can benefit from it. So first, let's recapture a bit what we talked about these 3 previous lectures. So we talked about in the first lecture about what is smart. So smart means connected normally, it's not intelligent. Often smart things can be very non-smart. But it includes everything that can automate and facilitate administration of a city, or in a larger scope as society. So we include logistics and transport and energy utilities and law enforcement and health services. So this is what's called a vertical view of a society. We divide the society into verticals, and we think that each vertical works within itself, and there is very little cooperation between these. And what we want to emphasize in these lectures is that a vertical view of a society is not the best way to create a smart city. So instead, the vision that we promote, a vision of a smart city, contains these aspects: ubiquitous access to devices, interoperable devices, ubiquitous access to data. And ubiquitous here means it's everywhere. We have smart services in all niches of society, which is a localization, you could say, the opposite of globalization. We also have ownership. Sorry about that. Okay, the ventilation. Air conditioning. Okay. So we wait for air conditioning to... Okay. In a smart city, in order for us to not create a smart city in the Chinese way, but Western style smart city, we need protection of privacy and the definition of ownership of information. This is crucial. And to sum all these things up, and what's the last step of this effort is to create open markets for data and for things. Without open markets, there will be no development, or very slow development. We talked about in the security section that, you remember Clapper, he in his report in 2016, he said that America's greatest threat is the Internet of Things. Among all the threats that exist to America, Internet of Things is the greatest threat. And so there is a reason for that. And if we look at the smart city, if we look at these verticals again, it's just all you have to do is imagine what happens if each of these vertical gets compromised or vulnerable and can be used either by criminal organizations or hostile interests. So it's a national security issue. And so we can ask ourselves, if this is the greatest threat and this is a matter of national security, why is the government not actively making sure that we do this the correct way? And unfortunately, often we have to have true accidents before we get legislative tools to protect things. So, for instance, in aviation, there is not a single regulation that hasn't had an accident before. So you remember that when you read the very thick books about aviation safety and security, there's a lot of accidents. The same thing will probably happen in our smart societies also. But governments must sooner or later consider this, and they must provide a strong foundation for our smart cities. Otherwise, well, building on a non-strong foundation will collapse. It's just how it will be. We discussed this, the three different ways to build systems. The instinctive way to secure a system is to seal it hermetically, or try to. Is this a good idea for smart city? Well, it will limit interoperability, so it will not allow us to reach this vision of a smart city. But if you leave it open, will also leave it vulnerable. And so the idea with this standard is to be able to create open and secure smart cities. So let's remember a bit what is needed. So smart things are stupid. There are no smart things. They are connected. And the one that controls the thing, if you have a lot of things, have a lot of leverage or power over the internet. And so we need to provide these smart stupid things, or stupid smart things, with decision support so they can make good decisions. We need to provide a way to define ownership, as mentioned. We need to have an infrastructure that recognizes the entire life cycle of a thing. It's not just manufacture and sell and forget. You need to maintain a thing over its entire life cycle. We need a way to, in our smart society, if we want to find things in all niches of society, we need to have a method to discover them. And we need interoperability. There is no point in installing a lot of devices if we are the only ones that can access them. And so the scope of this IoT harmonization contains all these things. We'll discuss them briefly today. In order to create an open, interoperable smart society. And there's also this is among one of the first standardization efforts that is actually managed open source, which is also quite interesting. So people interested in this can go into this repository and review and use the content. So the principal idea is to create a backbone that is globally scalable, efficient, not owned by anyone. It's not proprietary, so no one can claim ownership of it. But everyone can interoperate with everyone else if they agree. And as harmonization implies, we want to bridge different technologies, because there are so many technologies to use. In order for them to be able to interoperate, we need to bridge them. And this is also one of the things the IoT harmonization wants to do. We've discussed interoperability, and it might be good to review this image as an example of levels of interoperability. So when we talk about communication, we often mention the OSI 7-layered model, which goes from the lowest level physical layer up to data link layer, network layer, transport layer, session layer, presentation layer, and finally application layer. And there are multitudes of standards for each and every one of these layers. So you will hear that this is a standard, this is a standard, and you have to ask yourself, okay, on what level? So MQTT is a standard here up to level 5, for instance. But we need, for a smart society or smart city, we need standards all the way up to level 7 that defines the concept of a thing and how a thing works, and a good abstraction layer for that. So that's the point here. To join standards on lower levels and tie them together on the highest level of interoperability. And one of the benefits of doing it this way is that our effort can have a much broader audience. So we talk about vertical and horizontal markets, vertical and horizontal ways of viewing things. Today, if you look at a smart service, a manufacturer of a device must also often create the same service. And all the things between, they must host backend, and they must provide some form of, or use some form of operator, or be one yourself. It's a lot of work, and it's not what your interest lies. So as a manufacturer, you want to create a device, not necessarily host it and provide the service. There is no way a thing manufacturer can know all the ways the thing can be used for. In the same way, if you find a local niche and want to create a service, it's very difficult to find the economy to start to create your own devices, and you will seldom create them as good as other specialists will. So we want to segment the development. So this, if you look at the black vertical square, it contains more or less the same number of pixels as each of the layers here. So you can see the same effort, the same energy, or the same amount of resources allows you to create a much broader offering if you're a service provider, operator, or publisher, or device manufacturer. We discussed this, we will not go into this, we discussed this extensively last time when we compared different technologies, came to openness and security and flexibility and all these things. And we realized that certain technologies come with more features than others. And so when we want to create a backbone, we not only have to consider these features, but also choose where we want to build this standard on. So, more about this harmonization. You might remember, if you've been in this IoT business for some time, you might remember that there was an incredible hype around with IoT 10 years ago. And Ericsson was quick to remove their estimate of 50 billion connected devices by 2020. They said it 2010. And everyone has revised their estimates of how quick this development will be. So you have this Gartner hype cycle. So you have this peak of inflated expectations and trough of disillusionment. And then now we're coming into a plateau of productivity, which is a more realistic view. And so, but in order to get there, we need to understand why did everyone, including me and most others that worked with this, think that it would be so easy just to connect things and everything would just solve itself? Why wasn't it? Why didn't it create this boom everyone expected? And so, to understand this, it might be good to look at what could be the driving forces to build a smart society. If we want to build a smart society, what could motivate us to invest in this? And we've discussed this. Local support and knowledge. It's very difficult to create a global smart city solution that is applicable in all cities. I mean, it's just not. Each city is different, and it has its different needs. So you need local awareness, and this places requirements on development. Access to data was actually a good idea, and there has been a lot of work in this, but it was not sufficient. Another very important aspect we've talked about is cross-domain fertilization. If each vertical has to do everything over and over again, it's an extreme waste of resources. But if domains in verticals can interoperate and cooperate easily, it will create new types of opportunities that are not available today. And these opportunities will give rise to investments. We want to reuse existing equipment. So if we have 3 different use cases, all 3 wanting a temperature from the same location, it's inefficient to install 3 temperature sensors. It makes so we need to be able to reuse existing equipment. This is not possible in vertical situations. It's very difficult. Openness and transparency again has driven a lot of development, but it's not sufficient. It has to be simple and quick to do things. It cannot take half a year or a year to create a smart service. It needs to be able to be done in days or weeks. And to do this, we need to standardize. There is a complete lack of standards. As mentioned here earlier, if we wouldn't have standards for rail widths or sizes, we couldn't have trains traveling between countries. If we didn't have telecom standards, we wouldn't be able to talk to each other over boundaries and so on and so forth. And the same with internet. We wouldn't have browsers if there weren't standards for how to browse. And the same is true for smart cities. So the lack of standards for smart cities breaks the development. And the last but not least, the economy. So if you don't have a return on investment, the only way to invest in a smart city is by taxes. But if you create an incentive to invest, you have a natural process where development will flourish. And we have this discussion with politicians and others that this economic feedback is necessary, and it might be difficult for them to understand this concept because, well, it should be free. But then we have to ask ourselves, so if we invest in something, would we allow others access to it for free? Especially if it degrades, it puts load on our system, it degrades our own service, and they could compete with us without investing in hardware. Would we do that? The answer is evidently no. So any private enterprise, for them to share, there needs to be a market so that they can get a return on their investment, and different parties can share the costs. So understanding these, we need standards for all these levels. So there are standards for communication. That's good. So we have standardized ways to communicate. There are somewhat standards for representation, but very little standards for operation and security, privacy, discovery, all these things. Decision support and economic feedback. And that's the scope of IoT harmonization. So to solve this working group in IEEE, which is, I think, the largest standardization body in the world. I don't remember how many hundreds of thousands of members it has and member companies, but it's a very large standardization body. Some of you might have heard of Wi-Fi. It's an IEEE standard, or floating point numbers. It's IEEE standard and so on. So they look into this and want to create standards for the smart city. Now, in order to do this, they have to start somewhere. So they don't recreate everything from scratch. So they look, where do we start? And as you saw previously, we analyzed what exists, how many features there are, and then we begin more or less at the highest peak and build upwards. And so we've reviewed the different communication standards. XMPP, for instance, is the standard communication standard that has supports most features. So IoT harmonization begins there. It's globally scalable by default. It's decentralized, federated, and open, and also is proven. So it has this year 20 years of experience, you can say, in providing global services for billions of clients. It's designed within instant messaging, so by default, the default use case required security and privacy. The default use case for normal HTTP was to just fetch openly available academic documents. There was no apparent need for security and privacy. But in instant messaging, obviously, there is an apparent need. So it has a lot of security features, but not obviously all that is required. So IoT harmonization adds several features to what already exists. XMPP is also very, very flexible. It supports ad hoc networks and ad hoc communication, which basically means that beforehand you haven't defined what the users will do. Ad hoc means to the purpose for the instance. So when you design something, you can choose how to do it. You're not restrained. And so it might be good to repeat a bit the characteristics of XMPP. So it's called Extensible Messaging and Presence Protocol. So these are the cornerstones when they designed it. Extensible here means that the designers of the protocol understood that they couldn't foresee the use. So the protocol needs to support extensions without extensions colliding, so that different services can cooperate and coexist without clashing. Messaging means obviously send messages between. Now presence means that you need to know the state of the others, you can say in real time. So in instant messaging, you know if someone is online or offline. So this is also very useful information in other scenarios in smart city. You know what services are available to you and what state they are in. You might have heard of the Jabber project. That's how it started. So this name lives on. We talk about Jabber IDs, for instance. That's what that means is an XMPP address. And it's all based on XML. And that's the foundation of the extensibility. So XML is very easy to keep structured and semantically well defined. At the same time, everyone can extend it with namespaces. Some of the basic features: chat. It's globally scalable, just as mail, and is very robust. Some there are very well-known services, global services using XMPP. None mentioned, none forgotten. And communication works through brokers, just like MQTT we talked about. Brokers are servers, you could say, that only forward messages. They provide some basic services to the clients, such as maintaining accounts, which are the identities, who can communicate with whom. They route throughout the network and solve the topology problem, meaning that clients can communicate even if they are behind different firewalls. There are also serverless versions of XMPP, so you can communicate peer-to-peer if you need to transfer a lot of information. Basic authentication and encryption is all included. It supports 3 basic communication patterns, and from these 3 you can more or less build all others, and this makes it flexible. It's possible to send messages between anyone to anyone. That's called asynchronous messaging. You can request information, that's request response, and you can publish information and subscribers receive it. There are even 3 different types of publish subscribe, two available through extensions, and also multicasting. And that's just to start. IoT Harmonization provides more on top of that. Security again, not only does it authenticate all users, and there is encryption available, and this content-based authorization, which XMPP is the only communication technology to support. It also provides blocking and spam reporting mechanism, and through IoT Harmonization we have this provisioning. You can orchestrate large networks and end-to-end encryption. Now, when we design smart city systems, for us to be able to harmonize different technology, we need to know what types of communication occur. And this backbone need to support all these patterns. Otherwise, you restrict some technologies, and those won't be possible to harmonize with the rest. And typically, many communication protocols, they are designed around one pattern. XMPP is one of the exceptions, which allows many. And the reason for this is that often you want to have a protocol as lightweight as possible if you do it for very small devices, for small purposes. However, as technology advances, this requirement becomes less and less of a true requirement, and especially if we talk about the backbone, it's not a requirement at all. But asynchronous messages is the simplest form and most powerful in the sense that you can build everything from it. Anyone can communicate with everyone else at their own leisure. So there is no synchronization here. And the idea here is that all participants, they are peers. Peer meaning equals. There is no other role placed on them. And it's efficient in the sense that it's full duplex and everyone is identified. Some add on top of this quality of service. So there's a difference about of quality when you send a message. So you can send it in with a service called at most once. If it gets lost, you don't mind. You can have an acknowledge service to make sure the message arrives. That's called at least once. But there is no guarantee that it's actually delivered only once. It can be delivered twice. The acknowledgement can be lost, for instance. And then you have the third quality of service level, exactly once. That takes into consideration that acknowledgement can also be lost. And it's also called reliable messaging, and it's important in banking, for instance. If you count dollars, you want to make sure that the count stays the same in both ends, both the sending and the receiving end. If you support asynchronous messages, you can build support for the rest. Strangely enough, asynchronous messaging is not supported by many protocols. Request response is the most used pattern. It's for HTTP. Here you divide the participants into clients and servers. The client always requests and the server responds. As we've discussed, this becomes strange in IoT because often what we consider the server becomes the client, and the client becomes the server. But this is how the roles are made. And the basic use of this is obviously to serve. It was designed HTTP to provide articles on request. So HTTP is a good protocol for that use case. But it's very difficult to send from the server spontaneously information to the client, and you need to build proprietary things around it. There have been now standards like WebSockets that help you with this, but then it's no longer the same protocol. It's also half duplex, so you can send information in both directions, but not at the same time. And we can also see a problem arising from not requiring identity of the client. So only the server needs an identity. You go to the server and get the document, but since there was no original requirement of an identity of the client, distributed identities is very difficult in HTTP, for instance. Now, one of the bigger problems with request response for things is that you have to, if you want to know when a sensor value changes, you need to constantly request information from it using the request response. So a more efficient way is to just register your interest. This registration or subscription can include information about what you're interested in, not only the values, but also how often or under what circumstances. And then when something happens, the server sends you this information. This pattern is also called observe. And it's one of the reasons the constrained application protocol is so efficient, because it adds this to the request response patterns. And so it's very easy and a cost-effective way to monitor the state of a sensor. So this pattern is important. Now, remember this when we compare this to other patterns. It's the client that decides when it wants values, under what circumstances. For instance, if I have a temperature sensor, I might want to have a notification when it changes 1 degree, or I might want a notification when it changes 0.1 degree, or I want to have a notification when it reaches 20 degrees. And these are all different based on use case. And there is no way for the temperature sensor, especially when it's being produced or coded, for the manufacturer to know all the use cases it can be used for. So if you wouldn't do, if the client wouldn't define the limits, the temperature sensor would have to send it in the worst case, that is 0.1 degrees. So it would just spam the network in order to cover those use cases. Very inefficient. Multicasting, you might be aware of. You have different actors, they become members of a group, and everyone can hear what all the others are saying. So it's an efficient way to mass distribute or synchronize information. So it's used to synchronize clocks or synchronize updates, for instance, or communicate in clusters. So if you have clusters of servers that communicate, they keep synchronized using multicasting between them. But it's very difficult to have any kind of security mechanism in a group. So that's the difficult aspect. So encryption in groups is complicated. But it's efficient in discovery, for instance. So universal plug and play, you might be aware of. Each thing broadcast is present, and everyone in the network can listen in and connect. One way to make multicasting more versatile is publish-subscribe, using publish-subscribe. It's a similar concept. All actors connect to a broker, but information is published on topics and nodes. We discussed this with MQTT. And so not everyone hears everything. So a subscriber subscribes to certain topics and receives information when it's published on those topics. Now, the publish-subscribe pattern has become perhaps the most popular pattern in IoT, and also one of the reasons why it's so vulnerable. It's very efficient often to mass distribute information, but it's a bit more tricky, especially in certain protocols, to authorize access. It adds a degree of separation, which is good sometimes, between the publisher and the subscriber. But it's very difficult to federate, to make globally scalable. You can create islands, but creating a global federated network using publish-subscribe is very difficult. Queues you might have heard of, an alternative way to mass distribute. The difference between publish-subscribe and a queue, you could say, making it simple, is that the workers who replace the subscribers, only one worker receive each work item that is being published. It adds a degree of separation as well, and it's good for load balancing. It's mostly used in backend, not so much in edge processing for natural reasons, but to solve load balancing issues in backends, it's an important pattern. We're getting to the end, so bear with me. Federated brokers. This is the key for global scalability. If you look at global protocols, very successful, like mail, they're all federated. So federated means you divide into domains. HTTP also, obviously. Each domain is responsible for its domain of interest. Now, when I mention federated brokers here, the brokers themselves cooperate, meaning that clients connected to one broker can communicate with clients connected to other brokers, because the brokers themselves interoperate. Like mail, you can mail anyone in the world. They don't have to be connected to your mailing server. So it's a very important perspective, and it's the key to keep the infrastructure open. There can be no proprietor of the entire network. So the key features of using federated brokers, apart from global scalability, is also obviously resilience. No one can own the entire network. We solve the topology problem, as I mentioned. And as a side effect also, we have global distributed identities, which is very difficult in other protocols. So each participant has an identity that can be used for security reasons, for security decisions. Edge computing, we've talked about, is the concept that the cloud is only used for transport or basic services, like routers. You can call it software-defined networking. You can call it application layer, peer-to-peer, whatever. There are different names, but the point is the edges, the nodes at the end, do the communication and processing. The cloud is available as infrastructure. And it's also a mechanism to create globally scalable solutions, and it makes better use of existing processing power. It reduces risks and protects privacy, obviously. And in any decentralized networking, you can do centralized processing, but not the other way around. So it's a pattern that provides the least amount of restrictions, which is obviously important when we create a standard. So if we talk about communication pattern, we also want to talk about what kind of services are needed. We mentioned this. In the lab yesterday, we started testing one of these services, the registry, thing registry. But there are others also, like decision support, tokens, and smart contracts are required. We'll take this in turn. If you think of a mass production instead of proof of concept, you don't know at the time of production who will own the device, where it will be installed, and what it will do often. So a proof of concept, you can develop, you can connect things manually. There's a lot of work overhead, but it doesn't matter because you want to demonstrate the concept. But in a mass production environment, you want to produce millions of devices, but you don't want to do manual configuration yourself a million times, especially if you don't know where the things will end up. So you need to be able to match device with the owner afterwards. And Thing Registry does that. So a Thing Registry is a bulletin board where new things being installed register themselves. They register a conceptual identity. Conceptual identity meaning make and model of a device, serial number, such things. It can also be location or links to product information and so on. This information is understandable by humans. Network identity is often not so. But when the thing is installed and registers itself, it has a network identity, so the registry learns both the network and conceptual identities of the thing. The owner also knows the conceptual identity. It can be on a sticker, it can be on a display, or somehow the conceptual identity is transferred to the owner. And the owner can claim the device, can find it on the bulletin board in the registry by sending the same information. And the first entity that sends exactly the same information is considered the first owner. And then no one else can claim it. And the network identity is sent to the owner of the thing, and vice versa. The thing learns the network identity of the owner. And so the thing can ask the owner if something happens that it needs help with. Now, one way to transmit conceptual information can be using the IOT Disco Uri scheme. There's a link there for the definition of this scheme. It's basically a collection of tags. You can use any type of tags, string and numeric tags, and you can encode it as a QR code. So it's easy for an owner to scan this tag, and the application that scans the tag can then make the claim. And so the owner and the thing gets paired. The owner can also choose if the thing should be publicly searchable or not. Because once the thing knows the owner, it's secure for others to find it, because access to it can only be granted through the consent of the owner. So the next step, if the thing knows its owner, it cannot just ask the owner every time a new things happen, because the owner is probably a human, and humans cannot answer in real time when things need help. So decision support is required. So it's another kind of service that IoT Harmonization provides. So the decision support service knows also who the owner is. And it builds an internal database, you can say, of what is allowed. And so when a thing is requested something by someone, it doesn't recognize, it doesn't know what to do. It asks the decision support, the provisioning server, what can I do? The provisioning server looks in its rules collection, you could say. If it finds an answer, it responds. You can say yes or no, or a partial result. If it doesn't know, if it's the first time something happens, it just says no to the thing, but sends a message to the owner, who can, when the owner is available, respond. And through the responses, the provisioning server learns. And the next time the same thing happens, it knows how to respond. So it's a way to provision or orchestrate the system by the owner, not affecting in any way the operator. A very secure authorization mechanism. And you can control this way access to very detailed information in each device if you want to. Another service related to tokens is how do we solve distributed transactions. So if you have a network like this, you might have a client who wants to do something, it asks an intermediate node, who in turn asks other intermediate nodes, and they in turn ask devices for information. Now the devices, should they return information based on the identity of the intermediate node or the originator? And to solve this, the infrastructure provides tokens that are challengeable and based on public key infrastructure cryptography that the client can provide and the intermediate can distribute, and so the end devices can make decisions based on the original requester. It's obviously a very important feature that the infrastructure provides. Clock synchronization. If you have industrial Internet of Things applications, it might be important to synchronize events over the entire internet. And we need a way to synchronize events even though each node resides in different networks with different clocks and different local times and different clock synchronizations algorithms. So the IoT harmonization provides a mechanism to do that, and at a very high level of accuracy, often less than less than 1 millisecond accuracy. And so you can use this to synchronize clocks, for instance, or execute a command at a certain time, etc. And finally, smart contracts. We have discussed that to build an open society where entities can do things by their own volition, we need a way to make entities also responsible if they do things that are illegal. And in order to automate the IoT, we need to take this into consideration. And so IoT harmonization provides a way to define smart contracts and legal identities. So each actor can register a legal identity that is authorized, authenticated by public key cryptography. And smart contracts can define, for instance, requirements for access or requirements for being able to read the sensor, for instance. And as long as you approve the smart contract and sign it with a legally binding signature, you automatically get access to it. You don't need to have manual provisioning and decision making by the owner, even if the owner has provided the smart contract for the device. It makes provisioning even more automatic. And it's also the basis for this economic feedback. So if someone agrees to pay a fraction of some currency for access per month, and it's legally binding, the infrastructure can also count usage and provide information for billing and actual monetary transactions. So this is also included. To connect to this network, so we talk now, we create a big backbone. So you can connect to this network in different ways. You can either connect directly, you do so using XMPP, and then you can connect it through either TCP or HTTP WebSocket, and there is also an UDP experimental connection. Or you do it via what's called a concentrator, a thing of things. It can be a bridge, for instance, between protocols or patterns or technologies. It can also be the basis for the integration of backend services. And this concentrator concept is what allows this protocol to become a backbone. We can harmonize different technologies behind concentrators, which allow us to communicate with the devices on the other end as if they were connected directly to the network. The simplest form here is a programmable logical controller. It has embedded devices or logical devices inside. So the concentrator is connected to the network, but you can communicate with the logical entities inside as if they were separate entities. They can have different owners and can be provisioned differently. There's no difference between these nodes and other nodes on the network. You can use the concentrator as a bridge. Then it's only the bridge that is connected to the network, but the bridge also connects to other networks, for instance, an industry Modbus network, for example. And you can communicate with the Modbus devices as if they were connected to the XMPP network. You actually don't have to know the details. You can also integrate back-end systems this way. So you might actually communicate with devices that are not devices at all. They're just records in a database, for instance. So you can integrate existing systems this way also. Is it getting very heavy now? Getting more and more technical. So we were flying in the clouds. Now we're getting closer and closer to the grave in the day. So, but there are not. It's not much left, and there's coffee. So I'll skip this if you want. So then how can communication work? So another aspect that IoT harmonization has to consider is loose coupling. One of the goals is to contain sufficient information for both machine to machine and machine to human communication. What does that mean? That mean? It means that if someone invents a new device, you shouldn't have to upgrade the entire infrastructure with new drivers and new libraries. It should just work. So representation is designed in such a way that you can very freely define any type of sensor or sensor data or actuator. So it should be localizable. We have metadata describing the information. It's for humans and machines and loosely coupled, so you're not locked into a corner. The same with control operations. You should be able to define any type of control parameters, group them together, define validation information that is machine readable. At the same time, the parameter should be humanly understood or understandable. So that's the basic principle behind representation. When we come to operation, now we come close to this communication pattern that we have discussed. So how do you actually communicate with devices? And the simplest form is obviously the request response. That's where most people start. As you send a request and get a response from a device. That's a very simple case. But things can be slow, especially if you have concentrators that communicate with devices using very slow communication methods. So you can have delayed responses. At the same time, you have a requirement on the client side to be able to show updates in real time as quick as possible. And this is also taken into account, so you can have immediate feedback when something happens to the client. You can also have scheduled or queued operations, obviously. There might be a load, so you get all these notifications if something is accepted when it starts, when it's being sent. You can also have fragmented responses. You might have very, very large devices with thousands or millions of records, and you can send them asynchronously whenever they are available. You might read slow databases or use slow communication protocols and just report data as they become available. Provides a very nice end user experience to have immediate feedback. These are some examples. These are very simple examples provided in this repository that shows actual simplified communication. Now, event subscription is similar. You have a request response to subscribe, but then the device sends messages whenever the conditions that you have defined merit. And as with the request response, you can have fragmented events, you can have slow events, and so on and so forth. All is supported. And the difference here is just a very simple subscription and accepted, and you get messages as they arrive. So you can view this repository for more examples. Now, publish subscribe is also very simple. I've mentioned that XMPP supports 3 different publish subscribe patterns. Now, publish subscribe in some protocols like MQTT is very difficult to federate. So you publish information on topics, and this topic tree becomes very difficult to federate. One of the publish subscribe mechanisms in XMPP is called personal eventing protocol. And it actually converts each publisher into a federated node in this publish subscribe network. So it's actually a federated publish subscribe pattern. Actually the only one I'm aware of. And so each device can just publish the thing, and all connected entities that have shown interest in this information automatically receive it. And it's globally scalable. As you recognize here in the middle, it's the same sensor data representation as in all other patterns. The subscriber receives an asynchronous message like this with the same information and the exact information about who originated this information for security reasons. Control operations, the same thing, the other direction. Sending control operations, you just send. You can send it as a request response or asynchronous messaging. Very flexible. So that's more or less what I wanted to cover, the scope of the IEEE IoT harmonization. And I'm very happy that none of you have fainted, I hope. None has fainted on the other end, I don't know. But, as you know, this is a part of a Smart City series of lectures. We have 8 scheduled, or 8 planned lectures, 6 are scheduled. Next lecture is an introduction to encryption. So there we will not repeat the lectures we have had so far. We'll just talk about encryption for those that want to learn more about the different encryption algorithms and what they can be used for and when. The lecture after will go into the economic feedback models and how we can use this infrastructure to actually build systems that provide return of interest and value by sharing. And then we have 2 secret lectures soon to be scheduled. The labs also, you're welcome. We have had 4 labs. We've connected devices, we have chatted with them, we have published sensor data and used the thing registry. And next lab we will use this information in the registry to automatically find and detect devices that we can use for our control operations. Zero configuration. And after that, decision support. And as all this information also available in this book. So if you find this interesting, you can find all this information there. Now, questions. It will be very interesting to see. So it's a lot of technical information. please feel free to reach out. We can talk more about this over a cup of coffee. And thank you.
Thank you.